Einstein's general theory of relativity revolutionized our idea of gravity. It replaced the old idea of Newtonian gravity, where it was depicted as a force between masses. General relativity removed the concept of force from the description and added curvature in space-time. This theory is so powerful that from this one could obtain Newtonian gravity as well as explain the motion of planets in our solar system. So Einstein tried to explain beyond the solar system, and that is where he made a mistake which he will later call the greatest stupidity of his life. In 1915, Einstein published his field equations which relate the motion of mass and energy to the curvature of space-time. But Einstein didn't just get the equation accidentally. It was a result of a long and careful examination of key principles of physics along with the advanced mathematics of curved surfaces and of course agreement with the experimental observations. The equation, however, is deceptively simple. This one single tensor equation is in fact a shorthand for what's actually a system of 10 second-order partial differential equations relating mass and energy to the curvature of space-time. And the curvature R's themselves are a shorthand for more complex expressions. Einstein figured out that these equations matched up with Newton's law of gravitation for weak gravitational fields and speeds much slower than speed of light. The equations also correctly predicted the anomaly in the orbit of Mercury, which was unexplained by Newton's laws. After such success, Einstein tried to figure out what the equations had to say about the universe as a whole. Of course, all the matter and energy in the universe is far too complicated to put into the equations and have any hope of solving them. But if we zoom out enough, we can approximate the universe as having a roughly constant density everywhere and in every direction. Einstein was able to solve the equations for a very simplified universe with constant density everywhere. The 10 complicated equations reduced to just two simple ones. One says the curvature of space in the universe is proportional to the density, so more stuff in the universe means more curvature of space. And the other one says that the density has to be zero. Needless to say that this was a problem because it would mean that there's nothing in the universe. Einstein thought a little change in the equation might help in solving this. In his seminal cosmological considerations paper of 1917, Einstein showed that the general relativity could indeed give a consistent model of static universe. However, two assumptions were necessary. First, the universe was of closed spatial geometry like a three-dimensional sphere and had no beginning or end in time. Second, a consistent solution needed the introduction of a new term to the field equations of relativity. This new term, represented by capital lambda, is named as cosmological constant. It also doesn't change the results about how well the equations match up with Newton's law when gravity is weak or how well they predict the orbit of Mercury. Crucially for Einstein, the new term changes the equation for the density of the universe. Instead of saying density equals 0, it now says density is proportional to the new term. One puzzling aspect of this solution is Einstein's failure to consider the stability of his static universe. His analysis predicted a direct relation between the size of the universe and the density of matter within it. But what happened if the density of matter varied from time to time, as one might expect? In fact, it was later shown that the Einstein world is highly unstable against perturbations in matter density. It is strange that Einstein did not notice this aspect of his model universe. In 1922, the young Russian physicist Alexander Friedmann suggested that non-static solutions of Einstein field equations should be considered in models of the universe. Starting from the modified field equations, Friedmann derived two differential equations linking the time evolution of the universe with the density of matter and the cosmological constant. The first equation says, if the universe gets bigger, then it gets less dense, which makes sense. Here the term A describes the cosmic scale factor. The second equation says that the deceleration of the universe is proportional to the density minus Einstein's constant. That is, the stuff in this universe attracts itself gravitationally. So the universe would have a tendency to pull inwards on itself, slowing any expansion and possibly even contracting. Unless Einstein's constant was real and had a value big enough to balance or overpower the gravitational force. Well, Einstein did not accept this result And all of this changed in 1929 when the American astronomer Edwin Hubble published the first definitive evidence of a linear relation between the recession of the spiral nebulae and their radial distance. Many physicists accepted Hubble's results as evidence of a universe that was expanding on the largest scales. As a result, a variety of relativistic time-varying models of the cosmos were proposed. Einstein himself lost little time in abandoning his static cosmology at this point. He also abandoned the cosmological constant, stating that the term was both unsatisfactory and redundant. But this isn't the end of the story. Einstein's mistake gave birth to two most important concepts in cosmology. In 1931, Belgian physicist Georges Lemaitre made a bold advance. Noting that an expanding universe was undoubtedly smaller, denser, and hotter in the past, he suggested that our universe may have originated as a small primeval fireball, expanding and cooling over billions of years. This idea, later known as the Big Bang model of the cosmos, won favor with the discovery of several pieces of supporting evidence in the 1960s. The most important of these discoveries was a faint universal radiation left over from the infant universe known as the cosmic microwave background. We will discuss it in detail in another video. In 1998, observations of distant supernovas showed that universe wasn't just expanding, but the expansion was speeding up. Galaxies were accelerating away from each other as if some unknown force was overcoming gravity and shoving these galaxies apart. Physicists have named this enigmatic phenomenon as dark energy, as its true nature remains a mystery. In a twist of irony, physicists once again reintroduced the cosmological constant into Einstein's field equations to account for dark energy. In the current standard model of cosmology, known as lambda CDM model, the cosmological constant is interchangeable with dark energy. Astronomers have estimated its value based on observations of distant supernovas and fluctuations in the CMB. Although the value is absurdly small, it is significant enough to explain the accelerated expansion of space. The cosmological constant is thought to represent what physicists call vacuum energy. Quantum field theory states that even in a completely empty vacuum of space, virtual particles pop in and out of existence and create energy, which is a seemingly absurd idea, but one that has been observed experimentally. The problem arises when physicists attempt to calculate its contribution to the cosmological constant. Their result differs from the observation by a mind-boggling factor of 10 to the power of 121. That's 10 followed by 120 zeros. This is the largest discrepancy between theory and experiment in all of physics. But that's a topic for another video. Thank you for watching. I hope you liked it. Like and share this video. And to see such videos in future, do subscribe.